Good morning. My name is Steven Ortega,
And my name is Victor Pinheiro.
and today we'll be going over radiological sabotage analysis for high temperature gas-cooled microreactors. This is for our final nuclear nonproliferation policy for Dr. Alan J. Cooperman. In overview, we'll be going over small modular reactors and microreactors as well. We'll be going over the high temperature gas-cooled design as well as TRISO fuel, some avenues of attack, the defensive measures analysis, radiological consequences of an attack on a microreactor, and some of our recommendations. So let's talk about why small modular reactors and microreactors are gaining momentum. The answer lies in four key advantages that the designers are emphasizing. First, minimal security staffing. Passive features, specifically the robust TRISO fuel, are claimed to justify reduced on-site guard forces. Instead of having permanent armed security, designs propose relying on regional response teams for backup. Second, reduce exclusion zones. Because microreactors have smaller cores and lower power density, their potential source term is much lower. This supports shrinking emergency planning zones from the traditional 10 miles down to the site boundary, and sometimes even just a couple hundred meters outside of that. Third, there are diverse applications. Because unlike gigawatt scale plants, microreactors can power remote communities, military bases, industrial facilities, data centers, and mines that cannot accommodate large reactors. They open new markets and are touted as being easy to set up with minimal overhead. Fourth, factory sealed cores. Designs like the Zenith operate for up to 20 years on a single fuel load. No refueling, no fuel handling infrastructure, and therefore no associated security requirements on that end. Together, these features make microreactors attractive to policymakers, developers, and military planners. Let's go over some of the taxonomy for SMRs and microreactors. The IAEA has identified four main types of technology. The first is a pressurized water reactor. It uses light water as well as heavy water as both coolant and moderator at high pressure so it does not boil in the core. Heat is transferred to a secondary loop to make steam and drive a turbine. High temperature gas-cooled reactors, or HTGRs, use triso-coated fuel and a graphite-cooled core by helium gas, producing very high outlet temperatures for electricity and industrial heat with strong inherent safety features. This is going to be the focus of our analysis today. Molten salt and salt-cooled reactors either use liquid fuel dissolved in molten salt or solid fuel cooled by molten salt, operate at high temperatures and low pressure, and the salt can act as both coolant and in some designs a fuel carrier. And finally, liquid metal fast neutron reactors. They use a liquid metal coolant such as sodium or lead, operating with fast neutrons and no moderator, enabling efficient fuel use and in some designs, breeding of new fuel. So one of the things that is touted by these new companies is security by design in microreactors. Specifically, we're going to be looking at TRISO fuel and lifetime cores as additional enablers to HTGRs. TRISO fuel is considered robust because each fuel kernel is encapsulated in multiple engineered layers, typically a porous carbon buffer, inner and outer pyrolytic carbon, and a ceramic silicon carbide layer that together act as miniature pressure vessel and fission product barrier. These coatings can retain most fission gases and volatile radionuclides, even at temperatures far above those that will damage conventional fuel rods. And the radiation tests have shown very low particle failure rates under extreme conditions. Lifetime cores take advantage of this durability of very low power density. The core is loaded once at the factory with enough fuel to last 10 to 20 years of operation. In designs like X-Energy's Zenith and USNC's micromodular reactor, they are advertised to run up to about 2 decades without refueling. The sealed core approach eliminates routine on-site refueling outages and fuel handling, which reduces the risk there for security. It also simplifies staffing and fuel logistics and supports deployment in remote and military locations where bringing in fuel would be impractical. Now let's look at the HTGR reactor design. The one we are looking at here is a JAEA concept. A high-temperature gas-cooled reactor is a nuclear reactor that uses ceramic-coated uranium fuel, graphite as a moderator, and helium gas as a coolant to produce very hot outlet temperatures for power and heat process heat. The fuel is typically in the form of trisol particles embedded in graphite pebbles or prismatic graphite blocks. Fission in these fuel elements heats the surrounding graphite, and helium is blown through the channels in the core to pick up that heat. The hot helium then flows to a heat exchanger or gas turbine, where it transfers its heat back to a steam cycle or Brayton cycle to generate electricity before being cooled and recirculated back to the reactor in a closed loop. Because graphite has high heat capacity and helium is inert and single phase, the core heats and cools slowly and can remain structurally intact at very high temperatures, which supports passive safety features such as the ability to ride out loss of cooling events without fuel melting. The dramatic differences between traditional and microreactor designs become immediately apparent when we compare staffing and exclusion zones. These are some of the main drivers for microreactors. Large commercial power plants operate under strict regulatory requirements: a 10-mile plume exposure emergency planning zone, a 50-mile ingestion pathway zone, multiple licensed operators per shift, dozens of support staff, dedicated fire brigades, and armed security forces operating 24/7 to defend against design basis threats. High-temperature gas-cooled microreactors propose a fundamentally different model. Designers claim that the robust fuel and passive cooling features justify site boundary exclusion zones. With one or even no operators on site due to remote monitoring systems and autonomous functions, and no dedicated fire brigade because refueling hazards are eliminated with lifetime cores, and minimal or regional security forces rather than permanent armed guards to reduce costs due to the smaller impact if there were sabotage.
Okay, now I'll walk through the credible avenues of attack against the HTGR microreactor, focusing on sabotage pathways that are realistic rather than hypothetical. The first, and by far most consequential, is kinetic attacks on above ground components. Even though the reactor vessel itself is typically located below grade, the system that actually keeps the core cool are not. The helium circulators and cross-vessel helium ducting and the shutdown actuation equipment are all located above ground and mechanically complex and are not protected by containment structures. This matters because sabotage does not require breaching of the reactor vessel, and instead, an attack only needs to interrupt the heat removal pathway. Disabling a circulator or breaching pressurized helium piping immediately causes depressurization and loss of forced cooling, initiating a depressurized loss of forced cooling accident or a DLOFC. A key point here is that these components are industrial grade mechanical systems, not nuclear hardened structures. They're designed for efficiency and maintainability, not resistance to explosives or high energy kinetic attacks. From a sabotage perspective, this dramatically lowers the technical barrier. The second pathway is the cyber intrusion into plant control and data acquisition systems. HTGR designs rely heavily on automation and remote monitoring. If an attack spoofs temperature or pressure sensors, suppresses alarms, or interferes with the shutdown logic, it can delay the operator awareness at exactly the moment when a rapid intervention would be the most effective. Cyber attacks alone may not cause physical damage, but they are powerful force multipliers. A cyber intrusion that blinds operators or even a few minutes for even a few minutes create a window in which kinetic sabotage can succeed without resistance. The third pathway I'm going to talk about is insider assisted sabotage. This does not require a highly placed insider. We talked about this in class. Even limited insider knowledge, such as an access to routes, timing, or maintenance windows, or even familiarity with the control interfaces, can dramatically increase the effectiveness of an attack. Insider assistance primarily reduces uncertainty and detection risks, making otherwise difficult sabotage actions much more feasible. All three of these pathways coverage on the same operational goal. force a rapidly cooling failure faster than the system can or responders can react, which would cause problems. Next, we evaluate the feasibility of these attacks in a sabotage scenario. Not whether the sabotage is theoretically possible, but whether it is operationally realistic. The first feasibility uh, factor is physical accessibility. The critical components we identified are above ground, uh, externally accessible, and lack hardened enclosures. So an attacker does not need specialized nuclear expertise or equipment. Disabling mechanical integrity is enough to initiate a failure, even if these attackers do not have nuclear knowledge. The second factor is time. Uh, Disabling a helium circulator or a cross-vessel duct requires seconds to minutes, and in contrast, HTGR deployment models assume off-site response forces, which even under optimistic assumptions would require probably 8 to 15 minutes to arrive and intervene, which is obviously not soon enough. This creates a structural timing gap that favors the attacker. This timing mismatch is crucial. Sabotage does not require prolonged access. A short, intense action is sufficient to push the reactor into a thermal trajectory that cannot be reversed quickly. Third, underground sitting, underground siting does not prevent sabotage. We discussed this earlier with our proposal, and this made me realize that while reactor vessels themselves, or the reactor vessel itself is protected below grade, sabotage does not aim at the vessel. Instead, it targets the systems that prevent the core from exceeding the trisol fuel performance threshold. In other words, underground siting protects the wrong thing. Fourth, cyber-physical interaction increases feasibility. If intrusion delays detection, suppresses alarms, or confuses operators, the attacker's effective window expands. This interaction is especially dangerous in minimally staffed facilities, where situational awareness already depends really heavily on digital systems taken together. Uh, all these factors show how much sabotage is not an edge case. A small motivated group with realistic capabilities can probably disable cooling and initiate a DLOFC way faster than any existing response model can realistically reply to it. So the timeline opens up a lot, especially when considering these factors. And the current security model allows for this. So the response times would definitely not be enough to stop an attack, or at least a reversible attack. Next, moving on, we need to assess why existing defensive measures fail under sabotage conditions. First, underground siting. Uh, as we mentioned before, this is just a frequently presented as a security solution, but it primarily protects against a direct attack on the core. It does not protect the above ground systems required for heat removal. As a result, underground siting offers very, very limited protection against the most feasible sabotage pathways. Second, uh, passive safety and trisol fuel. Trisol performs exceptionally well in accident scenarios, but it is not sabotage proof. Once temperatures approach approximately 1600 degrees Celsius, fission product retention becomes uncertain. Sabotage seeks to deliberately push the system beyond the envelope, invalidating the assumption of passive safety. Third, automation and remote monitoring, which we already mentioned. Automation reduces staffing and operating costs, but it also creates cyber vulnerabilities. If sensor data can be spoofed or alarms suppressed, operators may not recognize sabotage until it's way too late to intervene. Fourth, minimal staffing models. We've discussed this at length, especially during our debates on the proposal for this project. And many HTGR deployments deployment concepts assume little or no on-site security at all. The assumption may be economically attractive because you're not paying for security staff, but it significantly weakens physical protection. Offsite response forces cannot intervene with the short time window required to prevent sabotage induced cooling failure. Overall, these defensive measures were designed to mitigate attacks, not deliberate attacks. When evaluated through a sabotage lens, uh, they leave very critical gaps. Furthermore, with policy implications, these findings are have for the physical security and time measures of it all have very important policy implications that we will discuss at length in a few slides.
Let's examine what a radiological release from a sabotage HTGR microreactor might look like in practice. We'll look at two bounding scenarios. Case A, worst case, severe core meltdown, and Case B, a more realistic degradation scenario with limited trisol particle failure where some, but not all of those safety features still function. In Case A, we assume essentially complete containment failure and extensive core damage. This is a scenario critics often have in mind when they hear the word meltdown or a sabotage. Even with trisol fuel, if the entire core is severely overheated, structural materials fail, and the containment boundary is breached, a large fraction of the fission products can be released to the environment. For a 1 megawatt thermal microreactor, that translates to on the order of 320 rem at 150 meters, which is easily high enough to cause acute radiation sickness in unprotected individuals. In this case, the zone where doses exceed 25 rem extends out to roughly 700 meters or more, and protective actions like evacuation and shelter in place would be required within that zone. Case B looks very different. Here we consider a more plausible sabotage event, targeted damage to a localized area of the core cooling system, with particle containment integrity preserved, therefore no runaway core melt. In this regime, trisol particles actually do the job they were designed for. The vast majority of fuel particles remain intact. Most fission products stay locked inside their ceramic shells, and only a limited subset of the particles fail and contribute to the release. At the same 150-meter distance, the resulting dose is about 53 rem. That level is still dangerous and will trigger protective actions, but it is orders of magnitude less severe than full core failure, as we assume in Case A. This is likely the case that developers tout as being safe and resistant to attacks. When we extend these calculations to different power reactors, the pattern holds. For both 1 megawatt and 10 megawatt thermal microreactors, 25 rem dose criterion, a common benchmark for emergency planning, can be satisfied with relatively small exclusion zones, ranging from a few hundred meters in the 1 megawatt case to 1.2 kilometers in the 10 megawatt case. The key takeaway is that the required radius is highly sensitive to two assumptions: how much of the core and containment are actually damaged, and how powerful the reactor is to begin with. This is why sabotage analysis matters. If real-world attacks look like Case B, as developers like to tout, limited fuel failure with constrained release, and a very small site boundary exclusion zone may be justified. However, if a credible attack pathway can push towards Case A, the security and emergency planning requirements start to look much closer to those of traditional reactors. However, given that microreactors have small source terms and small inventories of radiological material, it is likely that a successful sabotage will still have a smaller impact than a larger reactor. Furthermore, the lifetime core is a double-edged sword. Yes, it eliminates routine fuel handling, reducing staffing and safety vulnerabilities, but also means the entire reactor depends on that sealed core remaining intact for 10, 15, or 20 years of operation. Now consider where microreactors are targeted to be deployed: remote military bases, isolated industrial facilities, austere environments with limited infrastructure. If an attacker successfully damages that core through sabotage, whether through kinetic attack, cyber sabotage of cooling systems, or insider compromise, there is no field repair option. The replacement core alone costs $2 to $5 million, roughly 15 to 25% of the reactor's original capital cost. Getting a replacement design, manufactured, certified, and transported to a remote or conflict zone takes 3 to 6 months minimum. In an active military conflict, much more difficult and less likely to happen. And that's assuming the core is the only thing damaged. If the sabotage releases enough radioactivity to trigger an exclusion zone, site decontamination adds another 12 to 24 months of work. Full remediation of case A scenarios, with severe core damage with containment breach, can stretch into 3 to 5 years or longer. This creates a critical vulnerability. The microreactor's strength, a sealed, maintenance-free core, becomes a liability when that core is sabotaged. There is no graceful degradation, no swapping out fuel rods, no bringing the reactor back online quickly. It becomes a dead asset, an expensive replacement, and a contaminated site.
Perfect. Moving on, these findings have important policy implications. Firstly, the physical security regulations must expand their scope. Uh, Under current frameworks, many of the components most critical to sabotage scenarios are not treated as a security critical uh, regulatory as security critical. Regulatory standards such as the 10 CFR Part 73 should explicitly require protection of above ground cooling and shutdown components, as seen in the little blue square we have on our presentation. Emergency planning zones and exclusion distances are typically based on accident analysis. So, sabotage-driven DLOFC scenarios show that these assumptions may underestimate risk, particularly in densely uh, populated areas, as we can see in the red square right there, with revising sitting and staffing requirements. Thirdly, staffing and response models need reevaluation. If microreactors are to be deployed widely, especially outside traditional nuclear sites, then reliance on off-site responses forces is insufficient. So, on-site trained response capability may be necessary to enclose the timing gap. This has been discussed through the entire presentation, and it becomes very obvious upon more research that physical security and actual people in the facility is very, very important. And finally, uh, cybersecurity cannot be treated as separate from physical security. As we saw, several of the examples include the widening of the time gap in which attackers can cause damage to the facility, and sabotage scenarios exploit the interaction between digital and physical systems. So regulatory frameworks must reflect this integration. In conclusion, sabotage of HTGR microreactors is both technically feasible and operationally credible. And an attacker does not need to breach the reactor vessel by disabling exposed above ground components. They can force a depressurized loss of a force cooling and push the system towards the trisol fuel performance limit. Once that threshold is exceeded, meaningful radiological release becomes plausible, or even for small microreactor designs. The core issue is that current safety and security frameworks are built around accident scenarios, not intelligent adversaries, which could be very well the case for a potential attacker. The walkaway safe narrative holds for accidents, but it breaks down under the deliberate sabotage scenario. Until regulatory standards sitting assumptions, staffing models, and cyber physical protections are updated to reflect these realities. Widespread deployment of HTGR microreactors, particularly in civilian and urban environments, should proceed with great caution. To summarize, our analysis shows that sabotage of HTGR microreactors is both feasible and consequential under these realistic conditions. Even though the reactor vessel is typically underground, the system that actually keeps the core cool, including helium circulators, cross-vessel ducting, and shutdown actuation equipment, remain above ground, exposed, and lightly protected. Disabling these components can force a depressurized loss of force cooling, as we mentioned before, within minutes. Existing defensive measures such as underground sighting, passive trisol fuel safety, and remote monitoring were designed to address accidents, not deliberate attacks, as I mentioned. And the key takeaway is that the walkaway narrative is definitely not a safe assumption. Under physical security requirements, staffing models, and cybersecurity protections, we need to update these. Widespread deployment of HTGR reactors carries an unaddressed sabotage risk. Thank you very much. That was our presentation.